Vectors and Parametrics Day 2. The first thing I want to do is just make a couple of comments about some of the graphs that you should have seen in the homework over the weekend. I won't go over all of them today, but I'll just pick a couple of the types of functions that you should have taken a look at. One of them is rational functions, which are functions that are fractions, functions of the form, for example, x minus 4 over x minus 7. Functions like this are interesting because they typically have asymptotes, both horizontal and vertical, although not always. If you want to know a little bit about these functions, then you really should be asking about what the horizontal and vertical asymptotes are. If we go ahead and plot this function in Desmos, we'll find that the function looks like this. And I want you to notice two things. First of all, there's an x-intercept, well, a few things. First of all, there's an x-intercept at 4, as you can see. And that's not surprising because if you set this equation, if you set this function equal to 0 and solve, you'll find x equals 4 is the x-intercept. But maybe more importantly, you can see that there's this vertical asymptote right here, and that's happening because the denominator of this function is going to be equal to 0 at x equals 7, which is the location of the vertical asymptote. So if I type x equals 7, you can see that's where the vertical asymptote is. This function also has a horizontal asymptote, which is maybe somewhat less clear from the graph. It happens to be the horizontal line y equals 1. Now, how exactly can you see that? Basically, once we talk about limits, I'll be able to explain this a little bit more, but for right now, just understand that if the degree of the numerator and the degree of the denominator are the same, here these are both degree 1 polynomials, like they're both linear, then you will have a horizontal asymptote, which is the ratio of the lead coefficients of the two polynomials. What I mean by that is, for example, in the numerator here, the lead coefficient is 1, right? We don't really write the 1, but it's there. And the lead coefficient of the denominator is also 1. And so you're going to have a horizontal asymptote at the line y equals 1 over 1. To take another example, if I show you something like y equals 6x squared plus 5x plus 1 over 3x squared minus 2x plus 8. This has some kind of crazy graph. Interestingly, there don't seem to be any vertical asymptotes. I'll address that in a second. But there appears to be a horizontal asymptote at y equals 2, and the reason that's happening is that first of all, the numerator and denominator have the same degree. They're both degree 2 polynomials, so you will have a horizontal asymptote, and that horizontal asymptote will occur at the ratio of the lead coefficients. So the lead coefficient of the numerator is 6, the lead coefficient of the denominator is 3, so 6 over 3 is 2. The basic explanation for what's going on there is that as x becomes very, very large, as you go way off in the positive x direction, what's happening is that this term here, the squared term, is growing a lot more quickly than the other terms in the numerator, and so the entire numerator comes to be dominated by the 6x squared term. And likewise, in the denominator, the 3x squared term is growing a lot more quickly than the 2x, and certainly growing more quickly than the 8. And so for large values of x, this term is so much bigger than the other terms that it really just dominates them. In other words, essentially, for very large values of x, this function can basically be seen as just the ratio of these two terms, because these terms so dominate the rest of the expression for large values of x. And if you just look at the ratio of these two lead terms, the x squareds cancel, and you just have 6 over 3, which is 2. That's kind of the explanation for what's going on there. So that's a bit about rational functions. The other kind of function that I want to talk about very briefly was exponential functions. So exponential functions, of course, are basically functions where the variable is in the exponent, something like this, y equals 2 to the x, or y equals e to the x or something like that. They tend to look pretty similar. They don't have that much variety. They're less crazy in terms of their overall behavior than rational functions. If I take a look at 2 to the x, it has this classic exponential curve of blowing up to infinity very quickly in the positive x direction, but then decaying down to 0 in the negative x direction. You'll notice, and you probably did see in some of the problems, that if you put a negative sign in front of the x here, that actually switches the graph around. Of course, you know that putting a minus sign in front of the x creates a reflection across the y-axis, and this sort of reverses that behavior, where now you have the graph blowing up to infinity in the negative x direction and decaying down to 0 in the positive x direction. You can, of course, sort of put a multiplier in front of this thing, like multiply the whole thing by 5. That doesn't really change the graph in any significant way, except for the fact that it will change the y-intercept. By default, an exponential function has a y-intercept at 1, but if you multiply it by 5 or something, that will change the y-intercept. The other thing, and this is sort of less common, you could, if you wanted, multiply this by a negative number, and then it sort of flips the entire thing upside down, but that's not very common. Okay, so that's just a bit about rational and exponential functions, and I'll talk more about some of the other functions that appeared in that worksheet as we go on, but I don't want to spend all day on just graphing functions. So before we go into new stuff, I just wanted to clarify, and I mentioned this last time, but I just wanted to make it absolutely clear. On day 1, I basically was wrong about average velocity and average speed. Average velocity is displacement divided by the amount of time that's elapsed, and this is a scalar. This is like a magnitude, and average speed is distance traveled divided by time. So just as an example, if I go 2 kilometers north, then 5 kilometers west, let's find my average velocity and average speed. Well, I would say that there are 2 vectors involved here. One of them is the first vector going north, that's 0, 2, and then my other vector is the west direction, so that's -5, 0. And if you add those 2 vectors together, you get -5, 2. That guy is my displacement vector. Now, what is my average velocity going to be? My average velocity will be given by, oh, well, I have to actually say how long this took me, right? So let's say that this took me over 3 hours, okay? So what would my average velocity be if I did this amount of traveling in 3 hours? Well, average velocity, you're going to take the displacement magnitude, the magnitude of the displacement vector, which is the magnitude of this vector right here, and you're going to put that in the numerator here. So that's going to be the square root of -5 squared plus 2 squared divided by the amount of time that elapsed, which was 3. So that's going to be square root of 29 over 3. The units here would be, since the distance was measured in kilometers and the time was measured in hours, this would be in kilometers per hour. So that's average velocity. Average speed is a very similar idea, except rather than having the displacement, and displacement is really just about final position and initial position. The distance traveled is really sort of asking, how many steps did you take? And I went 7 kilometers north, and then I went 5 kilometers west. So obviously I actually walked, 7 miles is how far I actually went, right? Which is a little bit more than this number right here. So the numerator for average speed would just be 7 miles, and then just, the amount of time elapsed is still 3, so 7/3 kilometers per hour. So that would be the difference between average velocity and average speed. Really, the difference between these two ideas is average velocity really doesn't care about the path that you took. Like, you could zigzag all around, and average velocity is basically just going to say, okay, what was your net displacement? Like, what was your total change in position? Don't worry about some crazy just zigzag path. Just worry about what was the change in your position in total, and divide that by the amount of time t. Average speed though is actually caring about the path that you took, right? So if you went in one great big circle, then your displacement would be 0, and so therefore your average velocity would be 0, but your distance traveled would not be 0, and so therefore your average speed would not be 0. So that's just a quick clarification about that stuff. So we're going to talk about magnitude and direction of a vector now. This is new stuff. Magnitude we talked about last time, and the direction of a vector really refers to the angle that it makes with the positive x-axis. We've seen this idea. This is now the third context in which we've seen this idea. We have in polar coordinates of points in the plane. You can write a point in the plane in Cartesian form, or you can write it in polar form. And polar form is really about its distance from the origin, which is essentially magnitude, and its angle, right, which is essentially the direction here. And we saw this idea again in the context of complex numbers, right, where you have the magnitude or the absolute value of the complex number, which was just, its distance from the origin. And then you also had the angle made by the complex number, and that again is the same angle here. And we can do the same thing with vectors. So given a vector in the plane, we can obviously try to think of it in terms of the magnitude, which is just the length of the vector, and the direction, which is again just this same angle as measured from the positive x-axis, as always. So we'll do a couple of examples. So excuse me, sorry. So find the magnitude and direction of the vector v equals -5i plus 5 root 3j. So the magnitude is something that we've done before. Let's go ahead and take care of that. That's going to be square root of the components squared. So if I square -5, that gives me 25, plus if I square this quantity, the 5 root 3, that's going to be 25 times 3. And so this is just square root of 100, which of course is 10. So the magnitude is 10. The new thing here is, of course, the direction. How do you get the direction? Well, I think that one way of doing it is the same old formula that we used for polar coordinates, and that's to look at the tangent of the y component over the x component. So, the tangent of the angle will be equal to the y component over the x component. So we know that tangent theta will be equal to the y component, which is 5 root 3, divided by the x component, which is -5, which reduces to just negative square root of 3. And so what that's telling you is that your angle theta, which is, your direction, is an angle whose tangent is negative root 3. Root 3 is associated with, as far as tangent is concerned, that's some kind of pi over 3, or some kind of 60-degree angle, right? Of course, it's negative, and if you think about where this vector actually is, its horizontal component is negative, its vertical component is positive, so it's somewhere over here in the second quadrant, which means you're looking for the pi over 3 angle, or in degrees, the 60-degree angle, which lies in the second quadrant. And that's going to be, of course, either 2 pi over 3 in radians, or 120 degrees in degrees. So the direction would then be 120 degrees. So the magnitude of this vector is 10, and it's pointing in the direction 120 degrees. So that's magnitude and direction of a vector. Now, the magnitude and direction, let's do one more example. In the previous example, the tangent value was kind of nice. It was negative root 3. That's a tangent value that we know. As we'll see in this example, the tangent value that we get is not so nice. Let's first find the magnitude of this guy. So the magnitude, of course, is going to be square root of the sum of the squares. That's going to be 4 plus 9. So that gets us root 13. So the magnitude of this vector is root 13. As far as the as far as the direction, let's have a look at the tangent value. Well, I know that the tangent of theta has to be the y component divided by the x component, which of course gives you -3/2. That is not a very nice tangent value, and so we are going to have to use our calculator. Now, if you take the arctangent of -3/2, you will get an answer, but you have to be careful about whether it's the actual answer or the answer that you're looking for. So let's take the inverse tangent of -3/2, and my calculator is in degrees, so this is going to spit out degrees. -56.3 degrees. All right, well, that's fine, but right away I know that that can't be the right answer, because -53 degrees, so what did I say, -53, no, -56.3, excuse me, -56.3 degrees is pointing in this direction right here. That would be in the fourth quadrant. That is the wrong quadrant. This vector, like the first one, is actually in the second quadrant, so in fact I know that this is not the right answer, but as a matter of fact, you can get the right answer by adding 180 degrees, because the inverse tangent function can only spit out angles in these two quadrants between -90 and +90. This angle here certainly has a tangent of -3/2 as desired. The problem is that it's in the wrong quadrant. You'll get the correct one by adding 180 degrees. So theta equals -56.3 plus 180, which is 123.7 degrees. And so that is our direction of this vector. Okay, so in those two examples, what we did was we went from a vector given in terms of its horizontal and vertical components, and we went from that form to its magnitude and its direction. Now let's try to go the other way. Now let's suppose that somebody gives you the magnitude and direction. We want to be able to find the horizontal and vertical components. So given a vector's magnitude and direction, you can resolve it into its horizontal and vertical components via the following formula. So any vector v can be written in the following way. Any vector v will be the magnitude of the vector times the cosine of theta, where theta is the direction of the vector, the same angle we've been talking about this whole time. And that's I, the special unit vector I. So this guy right here is essentially the horizontal component of the vector. And then magnitude of v sine theta, this is going to be the vertical component of the vector. Now, why does this formula work? Well, it's really clear if you just look at the following diagram that I've got right here. Here's a vector v, and it's pointing in some direction. You can see that the angle is theta. Well, I claim that first of all, this blue vector down here is in fact the magnitude of v cosine theta I. Now, why is that true? Well, the length of this vector is definitely the length of v times the cosine of theta. That's really just right triangle trigonometry, right? If you think about what cosine of theta is going to be, that's the length of the adjacent side divided by the length of the hypotenuse. So that's telling you the cosine of theta would be the magnitude of this blue vector divided by the magnitude of this hypotenuse, and so therefore it follows that the magnitude of the blue vector is the cosine of theta times the magnitude of v. And then of course obviously this vector is purely horizontal, hence it's an I vector. It's pointing directly to the right. And then a similar argument tells you that the magnitude of this vertical vector is magnitude of v times sine theta, and of course it's a purely vertical vector, and so that's going to be a scalar multiple of j, the unit vector j. And it's very clear that, of course, adding these two vectors together gives you v, right? It's very clear that adding this blue vector with this green vector gives you the black vector v. And so that's where this formula comes from. And this formula is what allows you to decompose a vector given in terms of its magnitude and direction, allows you to decompose that vector in terms of its horizontal and vertical components. In a sense, this is just kind of yet another way of going from polar form to rectangular form, or from polar form to Cartesian form. It's a very similar idea. Just, again, don't get mixed up by the fact that there's an I here. That's not the complex number I. Let's just remember that. It's a completely different thing. So let's do an example. So suppose that a vector points 30 degrees west of north. Resolve the vector into its horizontal and vertical components. Be careful here because 30 degrees west of north, just because you see 30 degrees in this problem does not mean that theta is actually 30 degrees. It's not, right? Theta is the angle measured from the positive x-axis, and that's not 30. So watch out for that little wrinkle, but otherwise, it's very clear that, I need to give this vector a length, don't I? A vector which is, let's say it's 10 units long. There we go. So a vector which is 10 units long points 30 degrees west of north. Resolve the vector into its horizontal and vertical components. So how do we do it? Well, obviously, the magnitude of this vector is 10, right? We've been told that the length of this vector is 10 units long, so that's all squared away. And the angle, as I sort of mentioned before, it's not 30 degrees. Theta is measured from the positive x-axis. That's going to be 90 plus 30, which is 120 degrees. So with that in mind, we can use the formula that we have to write v in terms of its horizontal and vertical components. So so the vector v is going to be, here's the formula. Again, it's the magnitude of v times the cosine of theta I plus the magnitude of v times the sine of theta j. So that's our formula, and now we just need to plug in. So that's going to give us, all right, well, that's 10 cosine of 120 degrees I plus 10 sine of 120 degrees j. And now it's just a matter of evaluating. So that's going to be 10 cosine 120 is negative 1/2 I plus 10 sine of 120 is root 3 over 2 j, which once we simplify, we'll have our answer. So that's negative 5 I plus 5 root 3 j. And that is our vector v, written in terms of its horizontal and vertical components. So that's enough. So that's converting between magnitude and direction versus horizontal and vertical. I want to be clear though. Although you can do this, although you can switch back and forth between these two forms, I want to emphasize that the sort of I and J form, the horizontal and vertical form, is really the natural way in which we write vectors. Like, so I would not say that the two forms are equally good. The sort of horizontal and vertical component form of the vector is really the natural form of the vector. I just want to make that comment. So one big application of vectors is actually force. So it's a fact that force is a vector. Now, why is force a vector? Well, you can see that quickly by recognizing that when you apply a force in real life, like if you push a block in Zelda or something like that, it's not just how hard you push, right? But also the direction matters as well. And so that's telling you that whatever force is, it's something which depends upon both magnitude and direction, and that's sort of telling you that it's a vector. It is also true that if there are multiple forces acting on the same object, so say an object is being pushed around on the plane, and there are different forces acting on the object with different magnitudes and different directions, the resultant force, that is the net force, which is the force which results from all of these separate forces acting together, the resultant or total or net force is in fact the vector sum. So in other words, if you have several different forces acting on the same object, each of those forces is represented by a vector, and the total force which the object experiences, the net force, is given by the vector sum of those different forces. Now, why is that? It's basically an experimental fact. It's something that can be confirmed by experiment. It doesn't follow logically that the different forces add up that way. Maybe there's a universe in which forces add together in a different way, but in our universe they add together as vectors. So it's an experimental fact. So let's consider the following example. A block experiences two forces as shown, so you can imagine the block as being right here at the origin, and there are two forces acting on this object. One of the forces, F1, is acting with a strength of 150 newtons. N stands for newtons. Newtons is just a unit of force. You don't really have to know what it means exactly. And that force is acting 75 degrees off the positive x-axis. And then force 2 is acting with a strength of 200 newtons in the direction of 15 degrees off of the negative x-axis. And so what we'd like to do is to find the magnitude and direction of the resultant or net force, right? That's what we'd like to do. So how do you do this? Well, you've got to add these two vectors together, is what you've got to do, right? Because the net force, the resultant force, or the total force, whatever you want to call it, is the vector sum of these two vectors. Now, currently, these vectors are given to us in terms of their magnitude and direction. And adding vectors from their magnitude and direction form is not really something that we know how to do. We know how to add vectors when they are written in terms of their horizontal and vertical components. So what we need to do to sort of combine these two forces is we have to convert them to their, we have to resolve them into their horizontal and vertical components, right? So let's go ahead and do that. So F1, and I'm going to do this quickly. I'm not going to write out the whole formula, okay? So F1 is going to be, what is the horizontal component going to be? It's going to be the magnitude, which is 150 times the cosine of its angle, which is 75 degrees. The vertical component is 150 sine 75 degrees. You'll notice that I switch sort of randomly between writing vectors using the sort of the angle, the less than and greater than symbols, and the I and the J form. That's on purpose. These two things mean the same thing, right? This is the same thing as 150 cosine 75 I plus 150 sine 75 J. But you should be comfortable with both notations. That's why I'm switching back and forth. So if we ask our calculator what these are, 150 cosine 75 is 38.822. So that is my horizontal component, and my vertical component is 150 sine 75. And that is 144.88. Okay, great. So that's F1. F2, we have to be a little bit more careful. Oh, I should put vector symbols on top of these guys. These are vectors. So F2, we have to be a little bit more careful because even though you see this angle 15 degrees, you know that that is not the angle of F2, right? It's measured from the positive x-axis. And so the angle associated with F2 is in fact, it's 180 minus 15, right? So that's going to be 165. So it's 200 cosine 165, comma
200 sine 165. So what does that give us? 200 cosine 165. That's negative 193.185. And then the vertical component is going to be 200 sine 165. Oops. And that's 51.764. Great. So that's our two force vectors in horizontal and vertical form. And so now we can add these two vectors together. And so F net, in other words, the net force, the total force that's a result of the two forces acting, is going to be the vector sum of these two, right? It's going to be F1 plus F2. And that's very easy to do in horizontal and vertical form. So this is going to be 38.822 plus negative 193.185, I think it was, right? That's negative 154.363. And then the vertical component is 144.888 plus 51.764, 196.652. Did I do that right? Yeah. Great. And then the problem says to find the magnitude and direction of the resultant net force. So technically what I have to do now is I have to find the magnitude of this guy, which is going to be the square root of the sum of the squares, and then I have to find the angle of this guy, which you can figure out by thinking about the tangent of the angle. But I've already done examples like that, so I think that you can do that on your own. But just as a quick check, look, this vector is pushing 200 newtons this way, so it's a little bit stronger than the other force, which is only pushing with 150 newtons. So basically, the vector sum I would expect to be pointing somewhere over here, right? I would expect it to be pointing somewhere over here. So as a quick, gut check, when you get your angle, you should sort of ask, all right, does my angle actually put me in the second quadrant as expected? Okay, so we're just about done with today's lesson. The last thing I want to talk about is a very important concept from physics called equilibrium. There's actually different kinds of equilibrium, but we're not going to worry about that in this class. An object in this class is said to be excuse me, in equilibrium if the resultant force on the object is 0. Okay, so for example, if you have a single block and you have two forces acting on the block, and the two forces are acting with the same magnitude, but in exactly opposite directions, like two people just pushing against a block with the same strength, but pushing in the opposite direction, then, even though the object is experiencing different forces, the net force is 0, right? Those two vectors will exactly cancel each other out, and the net force will be 0. And so even though there are different forces acting on the object, nevertheless, the object is in equilibrium, which means the net force is 0. What that essentially means physically, you don't need to know this necessarily, but it essentially means that the object will not experience any acceleration, is what that means, in any direction. Now, so the key thing to understanding equilibrium is the following. Equilibrium is achieved if and only if the horizontal and vertical components sum to 0. Okay, that is the only way that equilibrium is achieved. In other words, having sort of net zero force in total, like a zero total force, really translates to having a zero force in the horizontal direction and a zero force in the vertical direction. In other words, if you have several different forces acting on an object, in order for them to cancel, the horizontal components of all those vectors need to cancel, and also separately the vertical components of all those vectors need to cancel separately. Okay, and so let's imagine the following example, and then we'll be done. So let's suppose that a block experiences 3 forces, and let's say that everything is measured in newtons. And here they are, but as you can see, some of the components of the forces are unknown, right? So x is the horizontal component of force 2, and y is the vertical component of force 3, and we don't know what they are. And here's the problem. If the block is in equilibrium, find the values of x and y. That's pretty simple because all you need to know is you need to say, hey, for this thing to be in equilibrium, the horizontal components need to add up to 0, and the vertical components need to add up to 0. So this just means that, okay, well, the horizontal components are 2, x, and 3. Those need to add up to 0, right? And so that's telling you right away that x is negative 5. Simple as that. And the vertical components need to add up to 0. So negative 3 plus 4 plus y, that has to add up to 0, which means the y is going to be negative 1, right? And yeah, and that's it. So that's it. As far as the homework, it's a little bit mix and match from some different problem sets here. So bear with me. Just do the exercises that I've listed here. Don't use the front of the packet as a guide because I think it's a bit ambiguous and I'm doing a bit of customization. So I'd like you to do exercise number 8 from classwork 1 of the packet. This was an exercise we told you to skip the first time around, but now that you know about forces, you can do it. Okay? And then I want you to do exercise 1 from classwork 2. Okay? You might notice that days 2 and 3 in the packet are kind of mixed up together. I'm not totally sure why that is, but basically I'm going to have you do, so you can see here's classwork 2 and 3, applications of vectors. So as I told you, you're going to do exercise 1, but then exercise 2 is something that involves stuff that I'll talk about next time. And then the homework is also mixed up together. There's just one assignment for homework 2 and 3, and so you're going to do some of these exercises tonight, and then you're going to do some of them next time. So the specific ones that I want you to do are, as I said, classwork 2, I want you to do number 1, and then for homework 2, 3, which is just, that page we were looking at before, you're going to do exercises 1, 2, 5, 7, and 8. That will not take you long, so I'm going to tell you that you might want to spend a bit of time memorizing some of the graphs that you found over the weekend. Try to do just a little bit of this each night. We're not going to need it right away, but as we get into parametrics, which is actually kind of the bulk of the unit, we don't spend that long on vectors. You're going to need to have those graphs memorized, basically, or at least you're going to need a pretty good sense of them. So spend a bit of time with them trying to memorize what they look like and their major features, intercepts and asymptotes and stuff like that. Okay, and although I'm out today, I'm testing negative for COVID. I'm pretty sure it's not COVID. I'm pretty sure I just have a nasty cold. So I'm expecting to be back at work tomorrow. So we should see each other then, and yeah, have a lovely day, guys. Oh, I always forget how to turn this thing off.